Hello students, in the last lecture you have studied about the point imperfections. Those were vacancies, interstitials, etc. Those were considered as a zero-dimensional imperfection. Now we will proceed further for one-dimensional imperfections, which are also called as dislocations or line imperfections. So as I told you, these are the one-dimensional imperfections. You can see in this image there are some kind of loops are there considered to be a thin lines which are representing the line dislocation, line imperfections. These line imperfections can be understood by two limiting lines. One, we call it edge dislocation, and second is the screw dislocation. In general, every crystal have both kind of dislocations. Rather than an individual dislocation, they are in a kind of a mixed type of dislocations, which is nothing but edge dislocation and screw dislocation within the crystal. Now to understand this one-dimensional imperfections, let's first consider the edge dislocations. Now to understand this edge dislocation, here you can see this is a perfect crystal, and in this perfect crystal we consisted of several atomic plane, right? Now if you see, this plane starts from top and continuing to bottom. This plane also starts from top and continuing to bottom. Now what will happen if this plane starts from top and limit here and do not continue to the bottom? So what will happen? This kind of situation you can see in this picture. This is a crystal where you are having a dislocations. So this plane is starting from top and not continuing to the bottom, and just next to this edge there are certain atoms shifted towards here. This is a kind of a stress relaxing displacement. So you can see there is an edge is formed inside this paper. This is a complete plane in two dimension like this, and that edge is formed here. So these are the imperfections which are present in the crystal. If you see some TEM images, you can see there are some dislocations here. The planes are coming but not continuing to the bottom. So this is one of the transmission electron microscopic image. Now this is another way to understand the edge dislocation. Again, this is a perfect crystal. This is a crystal which are having a dislocation. So there will be an edge has been formed inside this paper. This is a further in a two dimension. You can see in this is a two dimension image which you can see the dislocation. This is how we show this edge dislocation two dimensionally. Now if you see, when you study the vacancies like a dislocation, there are some magnitude of those vacancies. Let us suppose 10 into 10 to the power 2 number of vacancies are there. So to understand the magnitude and direction of these dislocation, we plot a two-dimension image of a crystal which is not having any dislocations. We want to know how much is the magnitude of that dislocation. First, to talk about the magnitude only. If there is a one half plane is missing, it is a one dislocation. If two half plane is missing, there are two dislocations. So in this crystal, you can see if I am starting from here to several interatomic spacing on towards my right. So I have traveled 1, 2, 3, 4, 5, 6 interatomic spacing towards left, and then again 1, 2, 3, 4, 5, 6, 7 interatomic spacing down, and then again 7 step towards left and 7 step towards again up. I am going clockwise. I am making a circuit which is clockwise. So I have reached to a position from where I have started. This is the case of perfect crystal. Now what happens if the dislocation is present in a crystal? Again, if I start from this point and several interatomic spacing towards right, then towards down, then again left, and if I am coming back, then I am not reaching to the same position from where I have started. To go to the same position, I have to go one interatomic spacing backward to reach the same position from where we started. So you can say one interatomic spacing. It means this is a something magnitude which we are talking about, which is one interatomic spacing. When you are having a one dislocation, then one interatomic spacing. If you are having a two dislocation, there could be a two interatomic spacing. So this is a very fixed invariant, because interatomic spacing is invariant. So this is a invariant quantity which we call it as a Burgers vector. So this we call it as a Burgers vector. And see, this is the clockwise circuit. If we make it anti-clockwise like this, then probably we will be one interatomic spacing backward and we will have to come like this. So once Burgers vector direction is this, clockwise, if it is anti-clockwise, Burgers vector direction is this. So what will happening means if Burgers direction should be same. So to define this, we define a unit vector t along this line, which we call a dislocation line, Burgers t. So if clockwise, the t vector will be inside the plane. If it is anti-clockwise, t vector will be outside the plane. So it is a unit vector. So this we call it as a Burgers vector. Now, just to understand how the edge dislocations are formed, basically this edge dislocation or screw dislocation, they are generally formed by shear forces. So this is the again representation of the planes, one matching with this plane, two matching with this plane. So they are nearly 9 crystallographic parallel planes, and you are applying a shear force to it. This plane, which we call it as a slip plane. So when we apply shear force, this plane will shift toward this side as it is shown here. Now you can say this is considered to be because only partial interatomic spacing is shifted. So we are calling this a partial dislocation. In the next image, if you see, this plane will be here. This fourth plane is a incomplete plane, and there is a distortion has been created just parallel to other parallel planes. So it is a complete translation, one interatomic spacing translation, and we are calling it as a full dislocation. And this is again is a Burgers vector, and this is a unit vector t. We call it edge dislocation boundary. Now you see, some students may be confused that the presence or you can say the extra half plane or a missing half plane is a dislocation. No, it is not. The distortion created by that additional plane or missing half plane is a dislocation, because here the distortion may be created and this side. So just above this plane, these are in the compressive state. Just below this plane, these are in the tensile stress state. So the distortion along that dislocation line, which is created by that additional half plane and missing half plane, that we call it as a dislocation. So distortion is just along here, along this line inside the paper. So this is what I mean to say as dislocation. As I told you, this is a unit vector t. We call it dislocation line. So this is an extra half plane, and this is the Burgers vector. This is how it looks. Now the second kind of dislocation is the screw dislocation. See, there are defects in the crystals. Now we are understanding those defects in a two different way. One is the edge dislocation and second is the line dislocation. So in the screw dislocation, if you see, if this is not a shear force is not here, then this will be a perfect crystal. Now you have twisted this crystal, applied a shear force like this. So what will happen? A step will be created here like this, as it is shown here. Now you see, if it is a perfect crystal like this, then we have made a circuit, Berger's circuit, and we will reach at the same position from where we have started in the case of perfect crystal. Now if you see here, just to close this loop, let us suppose I started here. To close this loop, I have to move one step. This is the step, one step to close this loop. So this is again a one interatomic spacing translation, and we are calling it as a Berger's vector. Now this line is called as dislocation line. Now if you see in the edge dislocation, here is the Berger's vector and here is the dislocation line, and Berger's vector is basically perpendicular to dislocation line, right? Here if you see, this is the Berger's vector, this is the dislocation line, and this Berger's vector is parallel to dislocation line. Now this is another way. See, if you see this graph, see this picture. So this is the one atom, this dotted one, and this is the another plane. This is one plane, this is another plane. Before the distortion, this plane will be matching with each other straight. Now there is a distortion, this plane here and here like this. This distortion is this one here. So you can see this position is shifted like this, and you can see this can be considered as a screw dislocation. So complete distortion along this line is a screw dislocation. And in this case, these are the other pictures of edge and screw dislocation to make you more clear. Now, if we see one-dimensional imperfection, there are things to remember. In the edge dislocation, there is an extra half plane. If extra half plane is above the slip plane, we call it positive edge dislocation. If extra half plane is below the slip plane, we call it negative edge dislocation. The same is with screw dislocation. And here it is perpendicular. Berger's vector is perpendicular to dislocation line. Here Berger's vectors are parallel to dislocation line. So along that line, just to understand, see the same picture, I'll give you another concept. So this is screw dislocation. Now let us suppose this in this case you are seeing it the surface, this surface, and here the another surface. One step forward on another surface. Now consider that there would be another crystal further. This crystal will be up to here. So you will see this is a kind of a extra half plane here. So you created a screw dislocation. See, planes are like this. What I mean to say, like this crystal is further extended. So this will be remain as a extra half plane in that crystal. So you can say one screw dislocation is also creating one edge dislocation. This is the way how you look at the dislocations. Now, so that one screw is creating an edge dislocation. So dislocation line is a kind of a curved line, say half of curved line. So one positive edge creating a screw, one screw creating another dislocation. So this is a kind of a dislocation loop, and along the dislocation line, except points. Except points means here this is the point. This is a pure screw dislocation. At point, pure edge dislocation. So in that between them, these are the pure edge, pure screw, but between them there is a mixed state of dislocations.